All right, I got a request for chapter 17, or chapter 21, problem number 17. Let's see if I can do this right. Basically, I'm going to work through this figure 2112. It's moving right to speed of 1.6 meters per second, 30 centimeters long, a resistance of 2 ohms. The magnetic field is 0.35 Tesla. The resistance of the U-shaped conductor is 25 ohms at a given instant. I want the induced EMF, the current, and the external force needed to keep the velocity constant. So let me get this over here, up on the screen. And I think I've got everything in here, right? I've got the U-shape, I've got 30 centimeters in length. Sorry, I had to erase a few things. Actually, this resistance equals 2.5 ohms, and the loop has a resistance of 25 ohms, and the field, right? Field strength is 0.35. Honestly, part A and part B, pretty straightforward. It's part C that's the tough part. So EMF, funny, right? I'm trying to find my potential difference. And for a moving conductor, if we looked at our AP Physics 2 equation sheet, would be magnetic field times length times our speed. So magnetic field, 0.35 Tesla. That's the unit we want to be in, Tesla's. Length, we're going to be at 0.3 meters. Remember, SI units. And then speed, 1.6 meters per second. And again, meters per second should just get us to that 0.3. So this EMF, right, 0.35 times 0.3 times 1.6 is 0.168 in our unit is volts. On B, we're wondering about current, and that's going to be V equals IR, but it's the equivalent resistance. So equivalent resistance, I've got a 25 and a 2.5 ohm resistor. So my equivalent resistance is just going to be this plus this. So they are in series, one after another, as far as current flow through here. So 0.168 divided by 27.5, that added together equals my current, which 0.006 amps. Okay. My last one is a chapter 20 deal. Okay. Chapter 20 deal, and it is the right-hand rule action, because the question to me is, which way is the current going, right? I guess this is actually chapter 21, and the right-hand rule as far as which way the current is going. So Lenz's law. My field, which is coming out, right? It's facing out of the page, is getting larger. That flux is getting larger because the area is getting larger. So if I do the right-hand rule thing, it's increasing, right? It's increasing. So what I want to do is oppose that change from back to forward. So forward to back, right? My current is going that way. So that's going to help us as far as what the force is. If I apply a force, a constant force to an object, it's going to keep accelerating. So I have to have opposing forces. Now I don't know which way the force is going. I need to have an opposing force, right? So that we can balance those out. So as far as direction, my current is going down, my field is out, so I've got a force acting. Let's again, field is out, current is down, so this force is acting this way. But what is that force, right? I want to apply a force to keep it a constant. So force should be current, right? Length of the conductor in the field times field strength, correct? So that goes back as far as direction, current direction, that's one way. We didn't really need to know the direction of the force and how to oppose it, but we did want to know current, length, and field strength. And I'm trying to think if there's anything else that we needed for that. Is that the correct equation? Let's just go back and double check. I'm going to go partial. I'm going to go AP2 equation sheet. And I'm going to go down. Let's see if we can get down here. Where are those EMF equations? Down. Magnetic force. I've got it right here. Current, length, and field strength. So I've got my field strength, I've got my current, and I've got my length. 0.006, 0.3 times 0.35. And that should give me my newtons times 0.3 times 0.35. So my force, to keep it a constant, 1, 2, 3, 6, 4 newtons. Okay? So I guess I didn't really need the direction. I really needed to know what force was driving that current carrying conductor in the field, right? As it's coming out, right? My current's going up, and or current's going down. That force is pushing it in, so I have to apply a force of 0.00064 newtons to make it go at a constant speed. And you didn't see any of that. So basically all I did was plug into my equation and solve. I think that's it.